Welcome to Calculus 1. So just to make sure that you're in the correct class, if you do not belong to Calculus 1 class number 12, go away now, okay? Okay, you have a chance to go away now. So let me introduce myself. So this is my name, Kwok-Wing Tsoi. One thing I want to make sure that is my surname is Tsoi. So call me either Dr. Tsoi, or you can call me my first name, I don't mind. But don't call me Dr. Kwok or Dr. Wing, okay? Both of them are not acceptable, okay? So be careful about that. And this year, I have scheduled my office hours on Mondays, 2 to 4, and Fridays, 3:30 to 5 p.m. Do you know what office hours are? So office hours are the time that you can come to our office and ask me any mathematics, okay? So because, I don't know, maybe you're too smart, but if you have any questions that you have after you take a class, then it's very common, it's very normal. And I don't know why, especially that happened to local students. They think that by sleeping with their question will disappear. It does not work like that, okay? So if you have a question, please come to me and let me help you, okay? Please, okay? Abuse us, okay? Abuse me and your TA nicely. And then, well, later you will meet your TA. You have TA class today. And then my email address, probably some of you know it already. So I put it there. So all the information that I put here will be available on NTU Cool. Don't worry about that. Another thing that you worry about or you're concerned is the grading scheme of class number 12. The grading scheme of class number 12, basically, half of your grade would depend on the examination in the last week of October. So half of your grade, 50% of your grade, will come from the examination in the late October. And for our class, we will have 2 quizzes, and in total, they will be worth 20%. Okay? I think they are going to happen in week 3 and week 7. Okay? You don't have to copy this. I will make this available, okay? Somewhere online. But something very special about class number 12 is we have something called semi-final examination. So basically, it's a fancy name for a longer quiz, okay? It's a quiz, but that will last longer, and will ask you basically half of the course, okay? So that will happen in week 5. So I think I run the semi-final examination for 2 years, and it has been very successful because students will think that by that time they have at least finished revising half of the course. So they don't feel that, in week 7 they have to revise from the beginning to the end, okay? So they're half of their course ready before the examination in week 5. And then with worksheet, okay, your TA probably have remind you should bring your worksheet for the TA class today. And then homework, we're written homework, and something called work. Your TA has told you that, right? Yeah, work, some online assignment that are very easy, okay, super easy questions, okay? And you can do it infinitely many times until you get them correct. So they are basically free credit that we give it to you. But you have to do it, okay? You have to do it. So the weighting for these 4 components are 15%, and the worksheet is 9%, homework 6%, and 6%. But if you add them up, I mean, your math is smart enough, you probably realize that it's more than 30%, right? So this component will be capped at 30%. So why do I do this? Because sometimes, for example, if you screw up the semi-final examination, then you have a chance to make up the difference, okay? Make up the losses, okay? Or in contrast, if you did your semi-final examination too well, then, well, you don't need to spend too much time here, okay? So this is the trade, okay? This is the trade, okay? So is that clear, okay? Is that clear? So I think I will run 1, 2, 3, 4 like this, okay? So you should get used to it. Okay, if you're happy, then we'll start, okay? We'll start. Because why I'm so rushed? Because you probably know that this Friday is a holiday. very unfortunately. Okay, so we got to start. We have a tight schedule. So let me start. So all of you have lecture notes, right? Hopefully. Okay, hopefully. If you have forgotten to bring your lecture notes, please write your notes on a piece of paper. So to be fair, this week, this is the first lecture, right? I'm not going to go into anything very serious. Indeed, this chapter is usually what I refer as baby mathematics, okay? So let us do some, it's really to clarify something you have learned in high school, and also for the fact that because some of you, it's the first time you learn mathematics in English, right? So take it as an English class, okay? Your English class is today. Functions and their limit, okay? So I assume all of you have seen a function before. Maybe the only thing is you have never seen the English translation of function, okay? But functions. So for example, a very basic function, basic example of function looks like, well, I just write it randomly. For example, f of x equals to x squared plus 1. Okay, this is a very basic example of function. I don't know how your school teacher defined what a function to you, but have you ever heard of a description of a machine turning input into output? Yeah, they call it function. So for example, in this case, x is the input. And x squared plus 1 is the output. So far so good, right? But what is very annoying in mathematics is that mathematicians, we love fancy names, okay? We are not satisfied by calling things input and output. We introduce fancy names for them. For example, in mathematics, we don't call things input, we call them domain. So instead of input, we call them domain. Domain is basically all the numbers at which the function fx is defined. Okay? So this is rather annoying in mathematics. We love fancy names. So similarly, in mathematics, we don't call output, we call them range. So these are all the possible outcomes of a function. Outcomes of a function. Okay? Is that all right? Okay? So I told you that today is an English class, okay? But one thing I want to remind you here is that it's very important you know that in mathematics, you don't learn mathematics like this. Okay, domain is all the numbers at which, blah, blah, okay? You don't learn it like this because this is not how mathematics work. It's a lot easier to understand mathematics by explicit example because this is how mathematics work. It's not someone wake up in the morning and then I wake up, oh, domain, okay? No, it doesn't work like that, okay? It's more like, okay, we have a bunch of examples that we have seen, we try to unify them. So therefore, example actually give you a lot more intuition into understanding a concept. And that is what we're going to emphasize in this course, okay? So let me do a very simple example of a function. So a lot of you, well, all of you, I suppose, okay, have seen this function, fx equals sine x. If you have never seen that, okay, go to a different course, okay? You'll probably go. There is a course called pre-calculus, okay? Then you can learn trigonometric function there. That's what I mean. So, so let us look at the domain. So in this case, what are the numbers that I can put into this function? Indeed, it's everything, because sine 1 is defined, sine 2 is defined, sine 100 is defined, sine 100 pi is defined, sine pi is defined. You can put any numbers into this function and it's defined. So the domain is every real number. But another annoying thing in mathematics is we like fancy notation. All real numbers has a fancy notation called R. Okay? So domain is not very exciting for psi function. What is perhaps more exciting about the psi function is the range, okay? So what are the possible output of this function? What can you get? You can't get everything, right? You can't, for example, no matter what x you put here, you will never get 2, right? Okay? Because you know that from baby mathematics, that psi is always squeezed between -1 and 1. So the range is indeed all the real numbers, or the x, such that x is between -1 and 1. And there is a fancy notation for a closed interval in mathematics. We use square bracket to denote it. So square bracket means nothing else than a closed interval. But now if you recall from school, when your teacher taught you the trigonometric function, the next thing they did was probably drawing the psi curve to you, right? I assume. And indeed, this is a very useful technique in doing, in understanding a function. That is, so let me write it down here. I call it skill. That is, it's convenient to think of functions graphically. Because very often when you look at the function, you may not have any feelings about it, but when you sketch the graph, you may understand it a little more. So for instance, of course, everyone knows how the psi curve looks like, hopefully, okay? So it's like psi curve, look like this. Sorry for my wonderful handwriting, okay? Wonderful drawing. And then from the graph, you can immediately tell the range of this function is between -1 and 1, because from the graph, you realize that the graph is always squeezed between, sorry for my drawing, 1 and -1. And this gives you the range of the function. So this is a useful thing to bear in mind. Indeed, I think in around week 6 or week 7, we will spend a whole week learning how to sketch the graph of a function. We do curve sketching, basically. So far, so good, right? Okay, so far, so good. As I say, probably you don't learn any new mathematics today, but then you probably learn some English today, so that is equally fine, okay, to me. Okay, let me move on to the next example. The next example is kind of interesting. I'm not too sure how many of you have seen this kind of example before. That is a function that is defined so-called piecewise. Piecewise defined function. Okay, so let's look at this function. So fx is defined to be just the function x when x is negative, and it's defined to be x squared plus 1 when x is positive. So depending on whether x is positive and negative, the function is defined differently. And then, okay, as usual, the domain, in this case, it's just every real numbers, again, because, well, our real numbers is either positive or negative, so you can put anything inside your function. So don't worry about that. What is more interesting in this case is the range. Maybe it's not obvious directly what the range is, but I previously mentioned that you can always look at the graph first, okay? So let us sketch the graph. okay? So, how is the function defined? When x is negative, it's defined to be just x. And I know that y equal x is just a 45-degree straight line. So when x is negative, you know this x, right? When x is negative, it's just a straight line. So let me draw it. Okay? Whereas when x is positive, it becomes a parabola because y equals x squared plus 1 is a parabola. So when parabola, okay, just in case you have never seen this term before. So this is the graph. However, mathematicians are usually a lot more picky because there is an ambiguity in this drawing. It's not obvious what does the point x equals 0 belong to. Does it belong to the straight line or does it belong to the parabola? So if you look at the definition of the function, when x equals 0, it belongs to the parabola. Therefore, we conventionally would draw it like this. So it belongs to a parabola, so we draw a solid dot here, and then we draw an open dot here to indicate that the point x equals 0 belongs to which part of the function. Now, looking at the graph, how do I determine the range? Well, range is the output. That means that you try to look at the y direction. The y direction, okay, is the output. If you look at the y direction, you realize that you essentially get every number that you like, except there's a little gap here, okay? There's a little gap here. So basically, the range is everything from -infinity all the way to, well, 0. Okay, this point is y equals 0. So it's 0. But remember, we're excluding 0 here. So this is an open interval. Open interval. But that's not all. Okay, after the gap, okay, we have a gap here. But after the gap, we start again from this is y equal to 1, and then all the way, okay, to infinity. So from 1 to infinity. But this time, 1 is inclusive. So we use closed interval. And you have probably seen that at school, that when you have two intervals together, you want to union them, then you use a notation called U. It means or, okay? It means or. So the output is either from -infinity to 0 or from 1 to infinity. So even this simple example demonstrates how the graph of a function is helpful for us to identify some properties of the original function. Is that all right so far? Okay, all right. All right. Okay, good. Too easy, too hard. It should be easy, okay? Okay, the last example, the last function I want to discuss here is a very important function that we'll meet again and again in this course. That is the absolute value function. Absolute value. The point of absolute value is it will turn everything into a positive number. For example, if you have -3, then you put absolute value, then it becomes 3. Or if you have -5, you put absolute value, it becomes 5. 5. But if you have an absolute value of a positive number, then nothing happens, okay? You have seen this before, right? Yeah, absolute value. It turns anything you put in into a positive number. But if you think over it, absolute value is also a piecewise defined function, depending on whether your input is positive or negative. So let me write it like this. So absolute value, it depends on whether you put in a positive number when x is greater than or equal to 0 or negative, the output will be different, okay? For example, if x is greater than or equal to 0, then absolute value, nothing happened, it's just x, okay? Nothing happened. In contrast, when you put in a negative number, you want to make positive. So how do we do that? We negatify it to make it positive. So, minus x. Is that all right? So, absolute value will turn anything into positive. If you put in a positive number, nothing happened, okay? If you put a negative number, then you have to negatify it to make it positive. So that will give you a positive number always, okay? Then in this case, the graph, okay, the graph looks like this. When x is positive, it's just y equal x, so you get a 45-degree straight line going upward. And then when x is negative, you get y equal minus x, so you get another 45-degree straight line going downward. So this is the graph. And then again, the domain in this case is any real numbers. However, the range, okay, the range, by the very definition, you always get a positive outcome. Well, when I say positive, I mean greater than or equal to 0, okay? So it means the outcome is always greater than or equal to 0. Or what does this notation mean? It means the interval from 0 to plus infinity. So this terminology will be used again in your worksheet 1, I think, okay? So when your TA discuss the first worksheet with you today, then you have some idea on this terminology. So far, so good, right? Hopefully, okay? Let me know if this is too slow. I can always accelerate, okay? I'm very good at that, okay? But I'm just worried that maybe it's not the mathematics, maybe it's the English. I want you to get used to my English first, okay? Because some people told me that I got a British accent, which I'm never aware of, okay? But maybe, okay? But your senior told me that after a few weeks, they will get used to it. I think normal people would say something like remember, okay? But we say remember, okay? So I mean, I wasn't aware of this, okay? Until some of your friends told me that, so your senior told me that. Okay, moving on. An important example of a function in this course is exponential function. So, well, it has a very fancy name called exponential function, but actually it's a lot easier than you think. Exponential function means function of the form fx equals to a to the x for some a positive, okay? And then the a here, we usually call it the base. By the way, if this is the first time you see this function in English, we call this a to the x, okay? I told you today you learned some English. If you're international student, okay? Then in Chinese, I think they call it this. Okay? So I cater both sides, okay? Just in case, okay? So a to the x. So I previously mentioned that to understand a function is a lot better to look at the graph. So let me give you an example of a graph of an exponential function. Here you are. Here I give you a graph of an exponential function y equal to 2 to the x. So what can you observe from the graph? So observation. What can you see from the graph? Apart from it's a curve, okay? What can you see? What is so special about this curve? Something very easy, okay? What can you tell immediately when you look at this curve? For example, it always goes up, right? So this is an interesting property already. So I call it second property. That is, this function is strictly increasing. Because it always goes up, okay? It's going up all the time, okay? Just now, we have learned domain and range, okay? Range. Can you tell immediately the range of this function? Do you realize that it's always pressure? It's always above the x-axis. Therefore, it means that the output is always positive, okay? So the range is all the strictly positive real numbers. So this is always positive. So do not underestimate this. We're going to use it again and again in the future, okay? So I want you to keep in mind that exponential function is, the range is always positive. And then what else? Okay, what else? When you were younger, when you first sketch some curve, your teacher would probably ask you, what are the x and y intercept, right? Where does it cross the x or y axis? And then in this case, you realize that it crosses the y axis here. So the y-intercept is the point 0, 1. Now don't underestimate this, huh? We are going to use it later. So the first three observations that I make here, probably a baby can look at, or can read that, okay? The fourth observation that I want to make is more relevant to calculus. That is, in calculus, we're interested in looking at the so-called asymptotic behavior. What do I mean by that? If you look at this curve, you realize that when x gets more and more negative, then it tends to 0. Asymptotic behavior, okay? And I will tell you how to spell it later, okay? I think I have it in my lecture notes somewhere. Okay, so as x go to minus infinity, it tends to 0. Okay? So this is fascinating. By just looking at the graph of function, I can immediately tell a lot of properties about it already. And indeed, each of these properties would be very important to us in the future. So don't underestimate that. And these are not just properties for 2 to the x. Indeed, these are properties of exponential function a to the x as long as the base is strictly greater than 1. Okay? So no matter it's 2 to the x, 3 to the x, 4 to the x, they share all these properties. Why do I emphasize that it has to be a strictly greater than 1? Because the behavior of the exponential function is a little different where a is less than or equal to 1. So let me eliminate a stupid case where a equals to 1, nothing happened, okay? 1 to the x, okay? You don't study this function. Because 1 to the x is just 1 all the time. So what would be more interesting is when a is strictly less than 1. For example, how about this? Half to the x, 0.5 to the x. When the base is less than 1, what kind of property can I tell? Firstly, let us sketch the graph. Do you know how the graph looks like? Of half to the x. You have 2 to the x here already. How about half to the x? Without a calculator. Don't take out your phone, okay? Don't Google it, okay? So how do you sketch this? You know 2 to the x look like this. Then how about half to the x? How does it look like? It refracted along the y-axis. Okay, let me tell you why. Because if you let fx to be half to the x, and you probably know that half is the same as 2 to the minus 1. And then by inverse law, then you know that 2 to the minus 1 to the x, you can combine them to make become 2 to the minus x. So, initially, you have the graph for y equal to 2 to the x. Then how do I obtain the graph of 2 to the minus x? That is, you replace x by minus x. And I guess you have learned at school, right? That is, the graph will be symmetric along the y-axis. Okay? If you have never learned it, we have a course this year called pre-calculus. It's discussed there, okay? Don't feel offended when you take the course of pre-calculus, okay? I mean, I think it's actually trying to help some students to catch up with the actual calculus course. So let me put it down anyway. So skill. That is the graphs of fx and f minus x are symmetric along the y-axis. Okay, so previously we have already known the curve, okay, y equal to 2 to the x, look like this. And now by refracting along the y-axis, then you get y equal to 2 to the minus x. Okay. Let me draw it prettier. This is y equal to 2 to the minus x. There's some funny noise. I don't know why that happened. Okay, but that's one thing I want to mention. That is, previously, as x go to minus infinity, then it tends to 0. But then an opposite behavior occurred for this exponential function. That is now, as x go to plus infinity, then it tends to 0. So the behavior of an exponential function will change when the base changes from greater than 1 to less than 1. Are you good at taking notes, okay? Then hopefully you can take notes fast. Oh, by the way, I always ask in the beginning of the semester, any of you have difficulty in distinguishing any different colors? Because my lectures, as you have seen, is very colorful. And then you don't have to let me know now. You can let me know privately. Because indeed, previously I got a student in the UK have color blindness. And then we can discuss what kind of color he can distinguish to help him or her, okay? So let me know privately. You don't have to let me know now. I make a lot of business for Muji. Because Muji sells very colorful pens, and then I got students getting all the fancy colors from Muji, and then to take my lectures. Okay, moving on. Let us do a very simple example here. That is here, I get 4 exponential functions, or more precisely, the graphs of 4 exponential functions. They are called what? Y equal a to the x, y equal b to the x, y equal c to the x, and y equal d to the x, respectively. And then the question asks you which one is the biggest and which one is the smallest. Can you tell immediately? Okay, let me try. Which one is the biggest? C, good, okay, so you know how to do it. So let me do it very quickly. So the way to do it is you need to introduce a magical line. The magical line is called x equals to 1. And then when x equal to 1, it cuts this curve at this point. What is this curve? This curve is y equals c to the x. So when x equals 1, y equal to c. So this point is c. In the y direction, this is c. Similarly, okay, this magical line will cut this exponential function at this point, and then this y equal d to the x. When x equal 1, you get d. So then this point is the y-intercept is 1. And then this point comes from the green curve, so it's A. And finally, this B. Then of course the origin represents 0. So hence, okay, C is greater than D, greater than 1, greater than A, greater than B, greater than 0. Okay? But why do I do this example? Not because it's fun, okay? There's a reason why I want to do that. I want you to observe these 2 numbers here. C is greater than D. So this is the curve y equal d to the x. And then when you increase the base, okay, when the base gets larger, then the curve will bend more towards to the y-axis. So this is what I mean, okay? When you increase the base from D to C, the curve will bend more and more towards the y-axis. So let me write down. So observation. Observation, I call it OBS, okay? Observation. That is when the base is greater than 1, then the larger the base, the more the curve will bend more towards the y-axis. Okay, so this is what we observe from this example. That is, when we increase the base of the exponential function, it tends more close to the y-axis. And this observation is going to be very important for us on the next page. Is that all right? Okay? So this is the observation that we make here. Oh, you see better when I move around. Okay? Better. And I think you guys are living in a lucky generation. Why do I say that? Because at my times, okay, actually I'm not a lot older than you, but anyway, just to clarify that, I'm not that much older than you. But the point I want to make is, at my time, I learned mathematics like this, okay? Then I have observation and things like that, okay? But now you're living in a computerized generation. You can watch a lot of fancy animation online. So I find one here. Okay? So basically, you can move around. So here, you get exponential function 1.7 to the x. Then you realize that when I increase the base, as I mentioned, you will get closer and closer to the y-axis. It bends more and more towards y-axis, okay? When the base increases. But what is special about this animation is that, can you see a straight line there? Do you know how do we call that straight line? Tangent, okay? Tangent, okay? Tangent. And this is going to be very important for us now to define something else, okay? So let us get back. Next page. So just now, we have seen an exponential function, okay? Exponential function, y equals to a to the x. And then in the animation, you have seen a tangent line. This does not look very tangent. Better, okay? This is a tangent line that happened at the y-intercept, at the point that I mentioned before, at CO1. And then in the animation, you have seen that if I change the base, if I increase or decrease the base, the tangent line will have different slope, okay? Now the question is, for which number a, for which value a, does the slope of tangent, the slope of the tangent equals to 1? Is the question, so let me put question mark, okay? So which base do you pick here such that this straight line, this tangent, is exactly 45 degrees? This is the question. You probably know the answer because the answer is in the title, right? But okay, this is indeed a very old piece of mathematics. This is discovered by Euler, a mathematician called Euler. So theorem of Euler. Do you know who Euler is? If you don't know, shame on you, okay? Kidding, okay? But you do physics, right? And also a lot of mathematics. You will see this name over and over again, okay? He is a very productive mathematician. So it turns out this number a that you need to pick is around 2.7, 1h, 2h, 1a, 2a, etc. Blah, blah, okay? And then for this reason, okay, because it's discovered by Euler, so instead of calling 2.7, 1a, 2a, 1a, 2a, we give it a name. So from now on, this number is denoted by the letter E, okay? When I say the number E, I mean the number 2.7, 1a, 2a, 1a, 2a, or in other words, by definition, is the base that you need to take in order for this tangent line to have slope equals to 1. That's the definition. The number E is the number you need to pick in order for this exponential function, the tangent here, has slope exactly 145 degrees. But I guess for some of you, this is not the first time you see the number E, right? Hopefully not, okay? But I was told that you don't learn E in this way. I think a more popular way to define E is this one, right? You have seen this before. E is defined to be the limit x go to infinity, 1 plus 1 over x to the x. What does that mean? It means that if you try to sketch the curve, y equal to 1 plus 1 over x to the x, Then as x go to infinity, when x gets very large, it gets closer and closer to one number. Somewhere here, right? Maybe not here, a little downward, here, somewhere here. Then it turns out this number is e. So I think this is a more popular definition of the number e. But now we have a trouble, right? I define e in a different way, and I don't see a connection between these two things, right? I mean, I define e as something about tangent slope of tangent line. You define e as a limit of a fancy function. But that is where the power of mathematics come in. That is, spoiler alert. So how can we make sure that the two numbers that we mentioned just now are really the same? That needs some actual mathematics. And indeed, we will prove that. We will prove by mathematics that these two definitions of the number e are indeed equivalent. That I can say, safe, okay? The number you define and the number I pick are really the same number, okay? It's not just, I choose the same alphabet. It's really the same number. But we'll do it, not today, but I think in week 3, okay? Now, also, this is a demonstration of perfect time management, okay? So let's take a break for 10 minutes, okay? And then we'll continue after 10 minutes. Okay, moving on. So I will apologize if today's materials sound too easy, but I mean, this is the first lecture, what do you expect, okay? It will get harder later, okay, if you want, okay? So don't mind about that. So the next thing I want to discuss with you is another class of interesting function. They are logarithm. So let me do a little recap on what logarithm does. That is, so basically you try to answer a question. If you fix two numbers, a and x, okay, fix two numbers, a and x, then you ask a question, a to the how many powers equals to x? Okay, you ask this question. Then this question is addressed by the function logarithm. So it turns out this question mark here is exactly the logarithm base a of x. So this is what we call logarithm of base a. So logarithm of base a. Okay, so let me do a silly example. For example, log 2 of 8. You ask yourself, 2 to the how many power equals to 8? That of course is 3, okay? So this is 3. Okay, let me do one more, just in case. For example, log 10 of 1 over 10 is, just to confirm, how many? Minus 1, good, okay? Just to confirm, okay? But immediately coming from the definition of logarithm, you have two basic identities. So two basic identities. According to the definition, a to the how many power is x, the answer is log a of x. Therefore, the first identity is a to the log a of x equal to x. You don't need to prove that. This is literally what it means, okay? Log a of x, it means the exponent that you need in order to obtain x from a. The second identity is log a of a to the x equal to x. Now, don't be too funny, okay? Think about that. Logarithm gives you the exponent, right? So why this is true? Basically, you ask yourself, a to the how many power, you will get a to the x. Then the answer, of course, is x. Okay. So these are not difficult. Fancy mathematics. Okay. These are really come from the definition, but they are quite useful. But if you think about it carefully, you will realize that there is a relation between logarithm with exponential function. So, relation with the exponential function. What do I mean by that? Let me do you an example, okay? So, if you consider the exponential function fx equal to 2 to the x. So what does this function do? You put in an exponent and give you an outcome. So you put in the exponent and then you have an outcome. So of course, for example, when you put 3, you get 8, okay? But 2 to 3 is 8, okay? But if you think about that, logarithm is kind of doing the opposite thing, because if you consider the function fx equals to log 2 of x, it's really you put the potential outcome and they will give you what exponent you need in order to obtain that outcome. So you put an outcome and they will get the exponent. For example, if you put 8, then the exponent that you need is 3. So it's doing an opposite thing. And then in mathematics, we describe function like this in pair with a special name. We call it inverse function. So let me put a remark here. So remark, that is exponential function and logarithm are inverse of each other. Okay? And indeed, this inverse function is exactly what your TA is going to discuss with you in the next lecture during the TA class. This is the materials of worksheet 1, okay? But I just give you a preview of that. And knowing that their inverse function are helpful when we sketch the graph, because this is also from worksheet 1. So this is the curve y equals to 2 to the x that we've seen before. Then we ask the question, how about the graph y equal log 2 of x? We know that y equal 2 to the x and y equal logarithm are inverse of each other. If we know one of the graph, then we can know the other one. Have you previewed the worksheet? Do you know how the other one looks like? How do we get the other one? By, you don't look at the worksheet. So how does the curve y equal log 2 of x looks like? Do you know that? Logarithm. How does the curve logarithm look like? Yeah, that one. Okay, that one. So it's exactly the one that you get when you reflect this curve by the line y equal to x. Then you will get the inverse function. So let me put a remark, okay? Remark. That is the graphs of y equal fx and its inverse function y equal f inverse x are symmetric along the line y equal to x, along the 45-degree straight line. And this we will discuss in worksheet 1, page 1. Worksheet 1, page 1. Of course, I know it. I wrote it. Okay? So, of course, I know it. Okay, so it will be discussed today, not with me, but with your TA. But I want to do a little remark here. That is a remark. You realize that as x, well, if you look at the logarithm curve here, as x gets closer and closer to 0, it gets more and more negative, okay? Indeed, you can get arbitrarily negative. So as x goes to 0, the logarithm goes to minus infinity. It doesn't matter. If you've never learned it, learn it today, okay? It's not too late. It's too late when you learn it next week, okay? So learn it today. Okay, so here I record 4 basic properties of logarithm. 1, 2, 3, 4. So I'm going to go through that very quickly. For example, one important property of logarithm is it turns addition into product. And then it turns differences into division. Okay? And then the next one is a very cute one. That is, you can take away the exponent and put it in the front. And the most important one, perhaps, because the first 3 one is kind of obvious, the last one is what we call base change formula. So you have log A of B, but this is of base A. In case you don't like the base A, you want to change it to something else, then it turns out this equals to log B over log A, and you can put arbitrary base here. So for any C. Just to confirm, you have seen this before, right? Okay. Again, they are discussed in gory details in pre-calculus, okay? So if you are not too sure why they are true, then let me advertise that course to you, 1 credit course, and then you get, well, you can learn all these materials again for free. But may I ask, have you ever seen a proof of this before? So for example, base change formula, okay? So I'm not going to prove everything for you, but then let us experience doing proofs together, okay? Because this is what a math course is about. So we're going to prove the base change formula. That is, we want to show log A of B equals to log B over log A, and then we can put arbitrary base here. WTS stands for want to show, okay? Okay. It's well known among mathematicians. Not too sure for muggles, okay? Do you know what muggles are? Do you read Harry Potter? Okay. Oh my God, I finally meet a group of students who have never read Harry Potter. Jesus, oh my God. Oh my God, I feel so old now. Okay, anyway. So we want to prove our identity, and then the usual approach is you start with the more complicated side. And I guess all of you agree, this is not more complicated, right? Okay, so we start from here. But before I do that, let me introduce names, okay? Let A equal to log C of A, and B equal to log C of B. Be careful. I didn't do any mathematics. Don't say that, oh, what is this, okay? I just give things names, okay? That's what mathematicians love to do. We want to make things look slightly more clarified. then we introduce more notation to it. This is not mathematics, okay? But then, by definition, when log C of small a equals to big A, that means that this is the exponent that you need in order to get the number A. So C to the power big A equals to A. The logarithm is the exponent that you need. And similarly, C to the big B equals to small b. Okay? So this is the left-hand side, right-hand side. And then when you look at the left-hand side, okay, left-hand side, what you want to get is log A of B. If you think about that, how should we approach that? The main difference between the left-hand side and right-hand side is that you don't have a C on the left. Therefore, a lateral idea that you will have is you try to eliminate C. Okay? Because you realize that the left-hand side has no C at all. But how do we do that? Okay, how do we do that? So let us start with B. B equals to, well, I know it here, B equals C to the B. How do I make C disappear? Well, I don't know how to make C disappear, but I know how to make C to the A disappear. Because C to A is small a. So let me do something very brutal and artificial. So make it look like C to the A, and then to the power B over A. Why do I do that? Because once I've done that, I can make C disappear. Because according to definition, C to the big A is small a. So this is really just A to the power B over A. So C disappear. I start with B, and then boom, 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 and I get A to the B over A. You guys are very... It's not that funny, right? It's not that funny. Okay, hence, the left-hand side is log A of B. But then, according to what I discovered just now, log B is really just A to the power B over A. But then, according to a property of logarithm that we discussed just now, when you have log A to the x, then you just get the exponent. This is because log A to the x is x. Okay? And then you realize that you're done because, well, what is big B? Big B, according to this, is log C of B. And big A, according to this, is log C of A. And it is the right-hand side. And we are done, okay? May I ask, okay, oh yeah, I want to ask two things, okay? That is, when you were younger, what is your favorite base for logarithm? Is it base 10? Forget about base 10, we never use it, okay? The most common logarithm that we use is base E, the number E that we've learned just now, the number 2.71828, okay? So we call it lateral logarithm. And then the notation is ln, okay? So don't be scared by ln. lnx is really logarithm of base E. And then we call it lateral log, or lateral logarithm. Just now I say two questions, right? May I ask the second question? How do you call this? Log. Good, okay? I want to hear log, okay? Not lum, okay? I don't know what kind of civilization taught people this column, this log, okay? Or you call it lateral logarithm. Don't call it in another fancy way, okay? It sounds ugly. It's a matter of taste, okay? But I want to specialize the identity or property that we discussed just now in lateral logarithm. So in particular, we have e to the log x is x. And then also, log e to the x is x. It's really the two basic identities that we discussed just now, but now with base equals to e. And the last one is base change formula. So now your favorite base in your life is base e. So you will always change any logarithm into base e. So base change formula. You have log a of b equals to lnb over lma. Okay? They are not new, okay? Basically, I specialize the property that I mentioned just now in lateral logarithm, ln. Okay, let's do the next example together. This is the last piece of baby mathematics that we're going to do together, then we can get into the actual subject of calculus. So solve the equation log x minus log 4x plus 2 equals to 1. What will you do first? What do you do first? Okay, what do you do first? Give up? No, okay, apart from giving up, okay? What are the other approach apart from giving up? What do you do? Hey, okay, good. You try to combine the logarithm. So because there is a property of logarithm, when you have difference, it will become division. So it will become log of x over 4x plus 2. And that equals to 1. Okay? And now we have a difficult question. Log of some garbage equals to 1, so what does that garbage equals to? This equals to what? E, good, okay? This equals to e to the 1. According to this property here. Okay? So log of something equal to x, then what does this something equal to? E to the x, okay? And now, having this equation, then using some baby algebra, you can probably solve it, okay? So, by using baby algebra, check. Then you will get x equals to minus 2e over 4e minus 1. Oh, but by the way, let me emphasize that I'm okay that you ask me this kind of calculation after class, okay? Even I make it sound very easy, but if you really encounter difficulty in doing this, ask me immediately, okay? Okay, don't let it go, okay? So, happy? Is that all right? Is that all right? Basically, it looks all right, except if you do this in an exam, you get no point, okay? This is wrong, okay? This is totally wrong. Are you aware of that? This is totally wrong. Why? Why? Correct. Because if you look at this number here, this is a negative number. However, the equation that you have in the beginning is log x, okay? And the log is not defined for negative numbers. So this number or this solution should be rejected, okay? So let me put it down. So be careful about this kind of thing. So warning. This is wrong, okay? And then because the logarithm, log of x, is only defined for x positive. So we have to reject this solution. We have to reject this solution. So hence, the correct answer to this question is there are no solution. So there are no solutions. So good. Some of you noticed that there is a gap. There's a trap here. Okay, there's a trap here. There's don't just solve and then get anything and then believe they're true. Okay, actually you need to check carefully whether they actually satisfy the original equation. But before I move on, may I ask just one more thing? Why? Why is logarithm only defined for x positive? So you know this, right? You know this, okay? So why? It's not because your teacher told you so, okay? And also, it's not because you put into calculator and it does not work, okay? They are not reasons, okay? These are not reasons, okay? So actually, it's relevant to what we mentioned just now. That is, what are logarithms? Logarithms are inverse function of exponential function. So let me put a remark here. Remark number one is actually what we mentioned just now. That is, exponential function and logarithm are inverses to each other. And then in the very beginning of this lecture, I mentioned that exponential function has a property. So if you have an exponential function, the domain is all the real numbers. However, the range, okay, the range, you get only positive real numbers. And on the worksheet they're going to learn today, that is when you have inverse of a function, then the domain and the range will swap, okay? So because logarithm is the inverse of exponential function, then what's the domain? The domain would be the range of its inverse. And then the range would be the domain of the exponential function. This will be discussed in worksheet 1, okay? Supposedly. Okay. So in particular, that's why logarithm is only defined, the domain is positive real numbers. So this concludes our baby mathematics session, okay? Hope you are satisfied with a little warm up on before we do actual calculus. So far, so good, right? It's not too difficult, right? Okay. If you find this difficult, then maybe you need to take pre-calculus first, okay? Or maybe you're not used to it, okay? Maybe you're not used to it because of the language. Also, if you're not used to listening to English, you can still drop my class, okay? Drop, okay? I think I take too many people. If you regret, it's still okay, okay? I'm not offended at all. Okay, now we get to the subject matter of calculus. But to study calculus, you need a language. The language that we need to define or make sense of calculus is what we call limit, okay, limit. I was told that you have seen limit before at school, but I will start from scratch, okay? I will start from complete scratch, so don't worry about that. So, intuitive definition. So I call it definition with a quotation. Why do I do it like this? Because do you have friends studying at the math department? If you have friends studying at the math department and you show them this is your definition of limit, they will slap your face, okay? So No, the reason is there are two subjects historically that occurred that are related to calculus. The first one, obviously, is calculus itself. The other one is called analysis. Some of you may have read something like epsilon delta, some fancy language like that. They are not calculus, they are analysis. Because later on in the history, so I probably heard of the story of Newton. So historically, calculus start with intuition, observation, and well, just working around with some explicit example. But later on in the history, people discovered that this is not enough. That's why they developed a whole new subject called analysis in order to fully justify the theorem that we try to believe in calculus. However, this is a calculus course, so we try to stick with intuitive definition, okay? So in my course, I'm not going to go through any fancy epsilon delta with you. Is that all right? Unless you're strongly against, then I would suggest you to take analysis instead of calculus. Is that okay? However, in order to give you some taste of doing fancy mathematics, okay, epsilon delta, in worksheet 2, you will learn a little bit from your TA the precise definition of limit. Or what we call mathematical analysis. Okay, just a very easy taste of precise definition using epsilon delta, that kind of fancy stuff. But in my course, I will try to do all this in an intuitive way, as intuitive as possible. But historically, also it goes like that, okay? If you don't want to do it like that, you should study a different course, okay? So let us look at definition. Rewrite the limit of fx equals to L as x go to A if fx get arbitrarily close to L when x gets sufficiently close to A from both sides but not equal to A. Oh my god, when you read that, what happened, okay? Okay, but let us introduce some symbol. So the limit x go to A equals to L means that fx get close to L when x get close to A. But there's one important point in the definition. That is when x tends to A, but it's not equal to A. This is very important. So x is not equal to A. X is just close to A, okay, but never equal to A. Let me do you an example, okay? You probably, well, this is a very easy example if you know what limits are, but there's a reason why I want to do that. The first reason is that, so let's look at this example. X go to 2 of x squared minus 4 over x minus 2. Firstly, we cannot read off the limit directly because you realize that you can't plug it, okay? When x equal to 2, the denominator will explode, okay? So the denominator will become 0. So the first thing I want to teach you is denominator means this, okay? And the numerator means this. So, I mean, depending on whether you know Chinese or English, you learn at least one thing from here, okay? Okay, so firstly, we realize that we cannot read off the limit directly because when we can't plug it, okay, directly into the function, the expression here. So what you usually do is to firstly, you factorize the numerator into a product, and then you discover that you can have cancellation. X minus 2 and x minus 2 cancel with each other. But what I want to highlight here is that the reason why you can do cancellation is really because by definition, when x go to 2, x is not 2. When x is not 2, so x minus 2 is not 0. And that's the reason why you can do cancellation here, okay? But then after the cancellation, it becomes so much simpler. Then it becomes a tautology. So when x tends to 2, then x plus 2 obviously will tends to 4, okay? 2 plus 2 is 4. So this is what I call pluggable. So our intuitive definition will tell us that as x goes to 2, then of course x plus 2 will go to 4. So that's how you calculate this limit. So easy example, okay? Let me do a different one, okay? Let me do a different one. Okay, let me do a different one. Compute the limit x go to pi over 2 of 1 plus cosine of 2x over cosine x. Before I do that, firstly, I know some of you are so smart, okay? No L'Hopital rule, okay? Do you know what is L'Hopital rule? Then no L'Hopital rule, okay? No L'Hopital rule. Forget about L'Hopital rule at the moment, okay? Don't tell me that, oh, I can do L'Hopital rule and then I can get it instantly. There are two reasons why I don't want you to use L'Hopital rule. Firstly, historically, L'Hopital rule come a lot later in the history, okay? Secondly, is I'm very famous for setting questions that are not L'Hopitalable. So I hope, you know L'Hopital rule is not universal, right? It's not something that kills everything. So there are a lot of examples for which L'Hopital rule does not work. If you don't know what L'Hopital rule are, congratulations, okay? Okay, congratulations. Okay, congratulations. Then you wouldn't be confused by anything. You can just learn my course from the beginning to end. If you know L'Hopital rule, at least in my experience, you will have a worse life with me, okay? Then people could know L'Hopital rule. So good, okay? And also, as I mentioned, this course is calculus. Calculus focuses a lot on explicit examples and computation. So besides discussing theory with you, I will also discuss some computational technique with you. So for example, look at this. 1 plus cosine of 2x over cosine of x. How will I approach that, okay? So it turns out, there is a universal trick that works almost all the time, not only for limit, but for the entire history of calculus. That is skill, okay? Let me call it skill. That is whenever you see the term 1 plus or minus cosine, then use the so-called double angle formula. Double angle formula. Which is cosine of 2 theta equal to 2 cosine square theta minus 1, or equals to 1 minus 2 sine square theta. By the way, depending on which civilization you come from, some people call it double angle formula, some people call it half angle formula. Same thing, okay? Same thing, okay? Don't be too fancy. It's not two different theorems, okay? So I call it double angle formula. So for example, in this case, you realize that, oh yes, I got the term 1 plus cosine somewhere. So I will associate with the double angle formula. So let's see how we do it. So we have limit x go to pi over 2, and then 1 plus, okay? I want to apply the double angle formula, but however, I have two versions here. I have either 2 cosine square minus 1 or 1 minus 2 sine square. Which one are you going to use? Which one? The first one, okay? The first one. 2 cosine square theta, x minus 1, and then over cosine of x. So some of you may be puzzled, oh, why do we use the first one? Because in doing limit, we love having cancellation. And then if we use this version, then we realize that the 1 in the beginning and the -1 at the end will kill each other, okay? And then that's good, cancellation happen. So after they kill each other, you're left with 2 cosine square over cosine x. And you will say, ha 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 ha, I can do cancellation, okay? So I can cancel the cosine x with one of the cosine x at the top. So I will end up with the limit x go to power over 2 of a much simpler expression, 2 cosine of x. And now it becomes a lot easier. That's why you can read off the limit directly by plotting into numbers, okay? So when you plot, then you will get 2 cosine of pi over 2, which is 0, good, okay? FYI. There's a research that we have done for last year's student. We discovered that if you're better in trigonometry, you do better in calculus, okay? So if you struggle with this kind of trigonometry, please revise it as soon as possible, okay? Don't leave it too late. We have a session on trigonometry in pre-calculus. You can watch that, okay? It's recorded by me, so you can watch me again, okay? Okay. The next example, I don't plan to go through a lot of details with you because I don't want to steal your TA job. Because basically, this is a very similar example in the worksheet. So let me put it that way. So exercise similar to the last question, grammatical mistake, the last question of worksheet 1. But I will give you some idea how to approach that, just give you some idea. So idea is to firstly simplify the expression tangent of arc cosine of x. This is called arc cosine, okay? This is called arc cosine. You will learn it in your TA class, okay? So it's the inverse function of cosine. It's the inverse of cosine. First. And I will also give you the answer. The answer is 1. So please, after today's TA class, try to do this by yourself. If you really get stuck, please come to my office hour ASAP, okay? Then I will fix you, okay? But I don't plan to steal the job of your TA, so that's why I don't discuss this here. So limit, probably some of you have seen that before, but then the next concept may be new to some of you. That is a more refined version to define limit. We call it one-sided limit. One-sided limit. So when x go to a, you have 2 options, right? You can either approach a from the left or from the right. And then depending on whether you are left or right, we have a different kind of limit. And they are called one-sided limit. So let me draw a number line. You have the number a. You can either approach the number a from the left or from the right. Before I do that, just to make sure, left, right, okay? Okay. I got students who are confused in the past, so I just want to make sure, left, right, okay? So left, right. So you can allow x to tend to a from the left, so in this way. And then notationally, we call it x go to a minus. But from the left, that means the less than a, so we call it a minus. And then on the other hand, if you approach a from the right-hand side, the notation is x go to a plus. Okay? We use the 1 plus because when you approach from the right-hand side, it means it's greater than a. Why do I say that there's a more refined way to discuss limit? Because of the theorem here. Okay? The theorem say that if the right-hand limit equals to the left-hand limit, and then they both equals to L, then you can conclude that the limit without one-sided, okay, without plus or minus, equals to L as well. This limit will exist and equals to L. So when left equals to right, then you can conclude the limit exists and equals to the value that they agree on. Okay, let us do an example. As I say, it's difficult to learn mathematics by just looking at it. It's a lot easier to internalize mathematics by looking at explicit example. So this is not a new example. This is one of the functions that I discussed in the beginning of today, a piecewise defined function. And we've seen the graph look like this. The graph is a straight line when x is negative. Sorry for my straight line, not very straight. Better. And there is a parabola when x is positive. And that is inclusive here and exclusive here. Okay? The first limit that I want to compute is limit of x go to 0 plus of fx. 0 plus means you approach to 0 from the right-hand side. So this x go to 0 plus. And then you realize that, even just from the graph, you realize that as x go to 0, getting closer and closer to the y-axis, the point that you end up with is this point. And what is this point? This point is 1. Okay? So that's why this limit is 1. However, if you want to understand this not graphically but algebraically, the way to understand it is you have x go to 0 plus. According to definition, approaching from the right-hand side, that means x is positive. It's greater than or greater than 0. Okay? It's greater than 0. And then according to the definition of the function, when x is greater than 0, the function is defined to be x squared plus 1. And now, it's more obvious why when x go to 0, then x squared plus 1, of course, will go to 1. So you get the same answer. So when x go to 0 plus, x is positive. And then analogously, the other limit, when x go to 0 minus of fx, so that means that x is negative now. But going, let me finish this example. When x go to 0 minus, then x is negative. Okay? So if you approach from the left-hand side, the point that you end up with is the origin. So that will represent the value 0. And that is also obvious from here because when x is negative, the function is defined to be x. But in particular, in this case, the right-hand limit and the left-hand limit do not agree. So the left-hand limit and the right-hand limit are not equal. Therefore, we conclude that, the limit, or the two-sided limit, of fx does not exist. I don't know who invented it, but there is a fancy shorthand for does not exist and widely used among students of calculus. They call it DNE. If you're too lazy, okay, you don't want to write 3 words, you can simplify it as 3 letters, DNE, okay? But the reason why the limit does not exist in this case is the right-hand limit and the left-hand limit are different. Okay, I will finish here today, and then Friday, don't come, okay? Enjoy your holiday, okay? Go home, okay? I'm not coming. And then I will see you next Wednesday at the same time, okay? See you next week.